The moment you try to predict where three things will be tomorrow, you discover the universe has secrets it will never fully reveal. I spent decades believing that if I could write down the right equations, measure the right forces, account for every push and pull, I could predict the motion of any object for all time. The mathematics seemed so clean, so certain. Two bodies orbiting each other, simple. The moon around Earth, Earth around the sun. I solved those problems completely. Then I tried three bodies, three masses, each pulling on the other two. The mathematics that worked so beautifully for two bodies shattered into pieces I could never reassemble. No matter how precisely I measured, no matter how carefully I calculated, the future became impossible to know with certainty. This was not a failure of my method. This was nature itself telling me that some truths live beyond the reach of prediction, even when every law is perfectly understood. Before we continue, take a moment to notice where you're listening from, and if this story stays with you, you're welcome to return tomorrow for what comes next. My copy of the Principia sits before me now, its leather binding worn smooth by decades of handling. The margins overflow with my own notes, corrections, and evolving thoughts. Each annotation tells a story of discovery, but also of the dangerous confidence that comes from early success. I arrived at Cambridge in 1661 as a sub-Caesar, paying my way by serving wealthier students their meals and cleaning their rooms. The humiliation stung, but it taught me that knowledge belonged to anyone willing to work for it, regardless of birth or wealth. Mathematics became my refuge from social embarrassment and my pathway to something greater than the farm my mother had planned for me. The plague years of 1665 and 1666 sent me home to Woolsthorpe, where isolation became the crucible of discovery. Sitting in my mother's garden, watching the apple fall, I began to see connections that had eluded natural philosophers for centuries. The same force that pulled the apple to earth held the moon in its orbit. The same mathematical principles that governed falling objects could explain the grand dance of planets around the sun. Those 18 months transformed me from student to discoverer. When I returned to Cambridge, I carried with me the inverse square law of gravitation and the mathematical tools of calculus. The universe suddenly made sense in ways it never had before. Every celestial motion could be reduced to elegant equations. Every planetary orbit followed predictable paths determined by mass, distance, and velocity. My first triumph came with predicting the return of what we now call Halley's Comet. Using my gravitational equations, I calculated that the comet seen in 1531, 1607, and 1682 was the same celestial visitor, following a precise elliptical orbit around the sun. When I announced it would return in 1758, many scoffed. Comets were considered omens, supernatural phenomena beyond natural law, but mathematics told a different story. The verification came after my death, as I knew it would. The comet returned exactly when my calculations predicted, cementing my reputation and proving that even the most mysterious celestial events followed discoverable laws. This success intoxicated me with the power of mathematical prediction. Next came the tides. For centuries, philosophers had noticed the connection between lunar phases and tidal patterns, but no one could explain the mechanism. Using my law of universal gravitation, I showed how the moon's pull created the bulges of water we experience as high tide. I could predict not just when tides would occur, but their relative heights based on the moon's distance and position. Each success reinforced my growing belief that the universe operated like a vast clockwork mechanism. If I could identify all the forces and measure all the initial conditions, I could predict any future state with mathematical certainty. God had written the book of nature in the language of mathematics, and I was learning to read that divine script with increasing fluency. The two-body problem became my specialty. Any system involving two masses attracted to each other by gravity could be solved completely. The Earth and Moon, the Sun and any planet, binary stars orbiting their common center of mass. The mathematics was beautiful in its elegance and terrifying in its precision. Given the position and velocity of two gravitating bodies at any moment, I could calculate their positions at any future time with perfect accuracy. Students came to Cambridge specifically to learn these methods. I developed a reputation for solving problems that had puzzled natural philosophers for generations. My mathematical approach seemed to unlock every secret the heavens had guarded. Eclipses could be predicted decades in advance. Planetary positions could be calculated with unprecedented precision. The irregular motion of the moon, which had frustrated astronomers for centuries, began to yield to my analytical methods. But even in those heady days of success, small discrepancies nagged at me. The moon's motion contained subtle irregularities that my two-body calculations couldn't fully explain. Sometimes it moved slightly faster than predicted, sometimes slower. The variations were small enough to dismiss as measurement error or atmospheric interference, but they persisted across multiple observers and instruments. I began to suspect that the sun's gravitational influence on the moon might account for these anomalies. After all, the moon orbits Earth, while Earth orbits the sun. The moon experiences gravitational pull from both bodies simultaneously. This was no longer a two-body problem, but a three-body system. My correspondence with Gottfried Leibniz during this period reveals my growing excitement at the prospect of extending my methods to more complex systems. Leibniz, brilliant though he was, shared my confidence that mathematical analysis could penetrate any natural mystery. We exchanged letters filled with optimistic speculation about predicting the weather, modeling the growth of populations, even calculating the optimal strategies for military campaigns. I remember writing to him in 1694, "If we can solve the motion of three bodies under mutual gravitational attraction, we shall have demonstrated that no celestial phenomenon lies beyond the reach of mathematical analysis. The universe will have revealed its fundamental clockwork nature, and natural philosophy will achieve the certainty of geometry." How naive those words seem now. How little I understood about the nature of the challenge I was about to undertake. The problem appeared deceptively simple. Three masses, each exerting gravitational force on the other two according to my inverse square law. The forces were perfectly understood. The mathematical framework was well established. I had solved countless two-body problems with ease. Adding one more body seemed like a natural extension of methods that had never failed me. I began with the Sun-Earth-Moon system, the most practically important three-body problem for navigation and calendar making. The Royal Society had commissioned me to improve lunar tables for maritime navigation, and I was confident that extending my two-body methods would yield the precise lunar positions needed for determining longitude at sea. My first attempts followed the same approach that had worked so well for two-body problems. I wrote down the equations describing each body's motion under the combined gravitational influence of the other two. The mathematics looked manageable. The physical principles were crystal clear. I expected to spend a few weeks deriving the solution and then move on to more complex applications. Those few weeks stretched into months, then years. The equations that had yielded so readily to analysis in the two-body case seemed to resist every mathematical technique I could devise. Where two-body problems produced elegant closed-form solutions, the three-body equations generated infinite series that refused to converge. Where two-body motion followed predictable conic sections, three-body trajectories twisted through space in patterns I couldn't capture with any mathematical function. The Royal Society charter bearing King William's seal arrived on a bitter February morning in 1695. The parchment felt heavier than its physical weight suggested, carrying with it the hopes of a maritime nation and the burden of lives lost at sea. I unrolled it carefully in my Cambridge study, reading the formal language that would change the trajectory of my work and ultimately shatter my confidence in mathematical certainty. By royal commission, it began, Sir Isaac Newton is hereby charged with the solution of the longitude problem, being the precise determination of position at sea through improved calculation of lunar motion for the preservation of His Majesty's ships and the advancement of navigation throughout the realm. The problem had been claiming English lives for decades. Ships setting out from Portsmouth or Plymouth with confident captains and experienced navigators would simply vanish into the Atlantic. Some ran aground on unexpected coasts, others missed their destinations by hundreds of miles, their crews dying of scurvy and thirst while searching for ports that lay beyond the horizon in directions they never thought to look. Latitude presented no particular challenge. Any competent navigator could determine north-south position by measuring the sun's height at noon or the elevation of Polaris at night. But longitude, east-west position remained a mystery that had defeated the finest minds of the age. The Earth's rotation meant that longitude was fundamentally a problem of time. Know the exact time at your home port and compare it to local noon, and you could calculate how far east or west you had traveled. But accurate timepieces couldn't survive the constant motion and temperature changes of ocean voyages. Pendulum clocks stopped working the moment a ship left calm harbor waters. Spring-driven mechanisms gained or lost minutes each day, accumulating errors that translated to hundreds of miles of navigational uncertainty. The only alternative lay in the heavens. The moon moved against the stellar background in predictable patterns, serving as a kind of celestial clock. If navigators could predict exactly where the moon would appear relative to specific stars at any given time, they could determine their longitude by comparing predicted positions with observed positions. This required lunar tables of unprecedented precision. The moon's motion had to be calculated not just for years in advance, but with accuracy measured in minutes of arc. A single degree of error in predicting lunar position could place a ship 50 miles from its intended course. Navigation demanded mathematical precision beyond anything natural philosophy had yet achieved. I accepted the commission with the supreme confidence that had never yet failed me. The moon orbits Earth while Earth orbits the sun. A three-body problem, certainly more complex than the two-body systems I had mastered, but governed by the same physical principles and subject to the same mathematical analysis. I estimated 6 months to develop the theoretical framework and another year to compute the detailed tables navigators would need. The Admiralty provided me with a generous budget for assistance and calculating machines. I hired the most capable mathematicians Cambridge could provide and set them to work computing ephemerides and testing different approximation methods. My study filled with charts, tables, and mechanical calculators clicking through endless numerical operations. The initial setup seemed straightforward. 3 bodies, 3 positions, 3 velocities. Each body experiences gravitational forces from the other two according to my inverse square law. The mathematics looked manageable when written in general form. The sun, much more massive than Earth or Moon, dominated the system's overall structure. Earth's gravity bound the moon in its orbit. The sun's more distant but powerful attraction perturbed both Earth and Moon in their respective motions. I began by treating this as a two-body problem with small perturbations. First, solve the moon's orbit around Earth, ignoring the sun entirely. Then calculate how the sun's gravitational field would modify this basic elliptical motion. The approach had worked beautifully for planetary motion, where the sun's dominance made other gravitational influences negligible corrections to the primary Keplerian orbits. But the moon situation proved fundamentally different. The sun's gravitational pull on the moon is more than twice as strong as Earth's pull. Rather than a small perturbation to a well-defined Earth-Moon system, the sun's influence represents a major force that cannot be treated as a secondary effect. The moon orbits Earth, but both moon and Earth orbit the sun, and all 3 motions are coupled in ways that resist mathematical separation. My first calculations produced lunar positions that disagreed with observations by several degrees. I refined the mathematics, included more terms in the perturbation series, and employed more sophisticated approximation methods. The agreement improved, but slowly and at enormous computational cost. Each additional term in the series required weeks of calculation by my assistants, and the convergence toward observational accuracy seemed to follow no predictable pattern. Letters from the Admiralty arrived with increasing frequency as 1695 became 1696. Ship losses continued to mount. The Merchant Marine pressed for immediate results. Naval commanders reported that existing lunar tables were so unreliable that navigators had given up using them entirely, preferring dead reckoning despite its obvious limitations. I found myself writing increasingly evasive responses to official inquiries. The problem was proving more complex than anticipated. Additional time was needed to ensure proper accuracy. Mathematical difficulties were being resolved through systematic analysis. Each letter bought me more time while revealing the growing gulf between my promises and my ability to deliver. The truth was that the 3-body problem was resisting every mathematical technique I could devise. Methods that had solved 2-body problems with elegant certainty produced only approximate solutions of questionable accuracy for 3-body systems. Worse, I was beginning to suspect that the problem might not have exact solutions of the kind I had grown accustomed to finding. My correspondence with Edmund Halley during this period reflects my growing frustration. Halley, ever the diplomat, suggested that perhaps perfect lunar tables were unnecessary. Navigational accuracy sufficient to prevent shipwrecks might not require the mathematical precision I was seeking. Why not develop approximate methods that worked well enough for practical purposes? The suggestion troubled me more than I cared to admit. My entire approach to natural philosophy rested on the belief that mathematical analysis could penetrate to exact truths about physical systems. If the 3-body problem could only be solved approximately, what did that say about the nature of mathematical knowledge itself? I pressed forward with increasingly desperate mathematical strategies. Power series expansions, trigonometric approximations, graphical methods, numerical integration techniques that pushed the limits of 17th century calculation. Each approach yielded partial success and ultimate frustration. I could improve the accuracy of lunar predictions, but I could never achieve the exact closed-form solution that 2-body problems had always provided. By the end of 1696, I was working 16-hour days, filling notebook after notebook with failed calculations. My assistants grew weary of computing endless series that seemed to converge toward no definite limit. The mechanical calculators wore out from constant use. Still, the moon's motion remained partially mysterious, following patterns I could describe but never fully predict. The stack of calculation sheets on my desk had grown to nearly 3 feet in height by the spring of 1697. Each page bore witness to another failed attempt, equations crossed out in frustration, series expansions that diverged into meaningless infinities, and approximations that worked for days or weeks before revealing fatal flaws. I kept them all, these monuments to mathematical hubris, as a reminder of how completely the three-body problem had humbled me. Let me explain why two bodies had been so tractable, and why adding just one more destroyed everything I thought I understood about celestial mechanics. When two masses attract each other gravitationally, they orbit around their common center of mass in perfect ellipses. The mathematics reduces to a single effective particle moving in a fixed potential field. I can write down the equations of motion in a few lines, integrate them analytically, and produce exact expressions for position and velocity at any future time. The orbital period, eccentricity, and orientation remain constant forever. Every question has a precise answer that can be calculated with certainty. The Earth-Moon system, considered in isolation, follows exactly this pattern. The Moon traces an ellipse around Earth every 27.3 days. I can predict its position centuries into the future with accuracy limited only by the precision of my initial measurements. The two-body solution is complete, elegant, and eternal, but the Sun changes everything. The moment I add the Sun's gravitational influence, the Moon no longer orbits Earth in a simple ellipse. Instead, it follows Earth's elliptical path around the Sun while simultaneously orbiting Earth in a pattern that shifts and wobbles in response to the Sun's varying pull. The orbit shape changes continuously. The plane of the Moon's orbit precesses. The orbital period varies from month to month. Every parameter I could hold constant in the two-body problem becomes a function of time in the three-body system. The mathematical complexity explodes combinatorially. Instead of tracking two positions and two velocities, I must simultaneously solve for 6 positions and 6 velocities, all coupled through gravitational forces that depend on the constantly changing distances between all three bodies. The equations fill entire pages with terms representing every possible interaction between every pair of masses. I spent months trying to reduce this complexity through coordinate transformations and approximation schemes. Perhaps I could solve the problem in the rotating reference frame where Earth and Sun appear stationary. Perhaps I could expand the Moon's motion as perturbations around its Earth-centric orbit. Perhaps I could treat the Sun's influence as a small correction to the basic Earth-Moon system. Each approach yielded partial success before revealing fundamental limitations.
The rotating reference frame simplified some aspects of the motion while introducing fictitious forces that created new complications.
Perturbation theory worked well when the Sun's influence was genuinely small, but failed when the three bodies approached certain geometric configurations where all forces became comparable in magnitude. Most troubling of all, I began to discover that tiny changes in initial conditions could produce dramatically different long-term behavior. If I started the Moon in slightly different positions or with slightly different velocities, the resulting orbital evolution would match for days or weeks before diverging onto completely different trajectories. This sensitivity meant that even perfect knowledge of the governing equations couldn't guarantee accurate long-term predictions unless I could measure initial conditions with impossible precision. Consider what this meant for navigation. A navigator observing the Moon's position could determine his longitude only if he could predict where the Moon should appear from any location on Earth. But if the Moon's future position depended sensitively on its current position and velocity, then small errors in astronomical observations would amplify over time into large errors in predicted lunar positions. The whole scheme for determining longitude through lunar observations would collapse if the Moon's motion was fundamentally unpredictable beyond some limited time horizon. My correspondence with continental mathematicians confirmed that I was not alone in this struggle. The Bernoulli brothers in Basel, Euler in St. Petersburg, and D'Alembert in Paris were all wrestling with variations of the three-body problem. Each had developed ingenious mathematical techniques, but none had achieved the kind of complete analytical solution that characterized two-body problems. Jacob Bernoulli wrote to me in 1698, "The problem of three bodies appears to exceed the power of human analysis, not through any deficiency in our mathematical methods, but through some fundamental property of the system itself. I begin to suspect that nature has arranged celestial mechanics so that complete predictability is impossible, leaving room for divine providence to operate within natural law." Even Leonhard Euler, whose mathematical abilities exceeded my own, confessed similar frustrations. His lunar theory, developed over decades of work, achieved remarkable accuracy through ingenious approximation methods. but it remained essentially an engineering solution rather than a mathematical triumph. Euler could predict the moon's position well enough for most practical purposes, but he could never explain why the system resisted exact analysis. The turning point in my understanding came during a sleepless night in December 1697. I had been working on a particularly stubborn set of equations when I suddenly realized that I was asking the wrong question entirely. Instead of demanding to know exactly where the moon would be at any future time, I should be asking whether such exact prediction was even theoretically possible. The mathematics suggested a disturbing answer. In systems with more than two gravitating bodies, the equations of motion could be written down perfectly, but could not be solved in terms of the familiar functions of mathematics. The problem was not that my techniques were inadequate, but that the solution literally did not exist in any form I could represent mathematically. This realization struck me with the force of a physical blow. For 30 years, I had believed that mathematical analysis could penetrate any natural mystery. The universe seemed to be written in the language of mathematics, and sufficiently clever analysis could decode any phenomenon. But the three-body problem was showing me that some truths lay forever beyond mathematical representation, even when the underlying physics was perfectly understood. I began to understand that the clockwork metaphor for the universe was fundamentally flawed. Clockwork mechanisms are predictable because they have been designed to eliminate sensitivity to small perturbations. But natural systems show no such design constraint. They can exhibit exquisite sensitivity to initial conditions while still obeying deterministic physical laws. The moon's motion was perfectly deterministic in the sense that its future state was completely determined by its present state in the laws of physics. But it was unpredictable in the practical sense that calculating its future position required knowing its present position with infinite precision. Since infinite precision was impossible to achieve through observation, long-term prediction became impossible to achieve through calculation. This distinction between determinism and predictability would haunt me for the rest of my life. Natural law could be perfectly deterministic while remaining practically unpredictable. Mathematical equations could completely describe physical systems while providing no method for solving those equations. Understanding and prediction, which I had always assumed to be equivalent, were revealing themselves as fundamentally different kinds of knowledge. The implications terrified me. If three gravitating bodies could defeat mathematical analysis, what hope did I have of understanding weather patterns, population dynamics, or the behavior of complex mechanical systems? The dream of a completely predictable universe governed by mathematical law and open to human calculation was crumbling before my eyes. The letters I exchanged with Caroline Herschel during the dark winter of 1698 reveal a man grappling with more than mathematical failure. Caroline, brilliant astronomer though she was, served as my confessor during those months when the three-body problem had shaken my faith not just in mathematics, but in the very nature of divine creation and human knowledge. I kept her letters locked in my private desk, away from the eyes of colleagues who still believed I possessed unshakable certainty about the workings of nature. My dear Sir Isaac, she wrote in January of that year, your last letter troubles me greatly, not for its mathematical content, which exceeds my understanding, but for the despair it reveals about the knowability of God's creation. Surely the Almighty did not design the heavens to be incomprehensible to the very minds he created to contemplate his works. Her concern was justified. I had written to her in a moment of weakness, confessing that the three-body problem was forcing me to question everything I had built my life's work upon. If the motion of three simple masses could defeat human analysis, what did this say about the relationship between divine will and natural law? What did it say about the purpose of mathematical inquiry itself? For 30 years I had preached that mathematics was the language in which God had written the book of nature. The elegant solutions to planetary motion seemed to reveal divine geometry at work in the cosmos. The precise predictions of eclipses and comet returns demonstrated that human reason could penetrate heavenly mysteries. Mathematical natural philosophy appeared to be a form of theology, uncovering the rational principles by which the Creator governed his universe. But the three-body problem suggested a more troubling possibility. Perhaps God had deliberately introduced elements of unpredictability into natural systems to preserve a realm for divine providence. Perhaps perfect mathematical prediction would eliminate the need for continued divine oversight of creation. If everything could be calculated in advance, what role would remain for the Creator after the initial moment of creation? This thought led me into territory that bordered on heresy. The mechanistic philosophy I had helped establish implied that the universe, once set in motion according to mathematical laws, would continue operating without further divine intervention. But if the three-body problem showed that even simple mechanical systems resisted complete analysis, Perhaps God remained actively involved in natural processes in ways that transcended human understanding. I found myself revisiting passages in Scripture that spoke of divine mysteries beyond human comprehension. For my thoughts are not your thoughts, neither are your ways my ways, saith the Lord.
For as the heavens are higher than the earth, so are my ways higher than your ways, and my thoughts than your thoughts.
Had I been guilty of intellectual pride in believing that mathematical analysis could expose all of God's methods? The clergy I consulted offered little comfort. Some welcomed my newfound humility as evidence that natural philosophy was finally acknowledging its proper limits. Others worried that if Newton's mathematics couldn't explain celestial motion, perhaps the entire scientific enterprise was built on false foundations. The Bishop of Worcester suggested that the three-body problem might be God's way of reminding natural philosophers that some truths were reserved for divine revelation rather than human discovery. But I couldn't accept such easy resignation. The physical laws governing three-body motion were perfectly clear. Each mass attracted every other mass according to the inverse square law, with a force proportional to the product of their masses. The mathematics was unambiguous, even if it couldn't be solved analytically. The problem was not that God had made the system mysterious, but that he had made it more complex than human analytical methods could handle. This distinction became crucial to my evolving understanding. Complexity was not the same as mystery. The three-body system was completely deterministic in the sense that its future states were entirely determined by its present state and the laws of physics, but it was practically unpredictable, because calculating those future states exceeded human mathematical capabilities. I began to see that predictability and understanding were different kinds of knowledge. I could understand the physical principles governing three-body motion perfectly while being unable to predict the detailed consequences of those principles. Understanding revealed the mechanisms at work. Prediction required computational power that might be beyond any finite mind. This realization opened new questions about the nature of divine knowledge itself. Did God's omniscience include perfect knowledge of every future state of every physical system? Or did divine providence operate through ongoing interaction with creation rather than through perfect foreknowledge of predetermined outcomes? Some theologians argued that perfect divine foreknowledge was necessary to preserve God's sovereignty over creation, but others suggested that a God who chose to create unpredictable systems might be demonstrating a different kind of sovereignty, one that included the freedom to respond creatively to genuinely open futures, rather than simply unfolding a predetermined plan. My correspondence with Leibniz during this period reveals how these theological questions intersected with fundamental issues in natural philosophy. Leibniz maintained that the universe was completely rational and that all future states could, in principle, be calculated by a sufficiently powerful mind. He argued that the apparent unpredictability of three-body motion reflected only the limitations of human mathematics, not any genuine indeterminacy in nature itself. I found myself disagreeing with my old rival on grounds that would have seemed impossible a few years earlier. While I agreed that nature operated according to rational laws, I was beginning to suspect that rationality might include irreducible elements of unpredictability. Perhaps a perfectly rational creator would design systems that exhibited both lawful behavior and practical unpredictability, preserving room for genuine novelty within the constraints of natural law. The psychological toll of these realizations was enormous. I had spent my adult life believing that mathematical analysis was the royal road to truth about the physical world. My reputation rested on demonstrations that human reason could penetrate the deepest mysteries of nature. Students came to Cambridge to learn methods that promised certain knowledge about natural phenomena. Now I was confronting the possibility that the most fundamental systems in nature might be essentially unpredictable, not through any failure of natural law, but because of the intrinsic complexity that emerges when simple laws govern multiple interacting components. The universe might be simultaneously lawful and unpredictable, rational and surprising, determinate and practically unknowable. This crisis of confidence affected every aspect of my work. I found myself questioning not just the three-body problem, but all the mathematical predictions I had made with such certainty. Were planetary positions really as predictable as I had claimed? Might small perturbations accumulate over centuries to produce orbital chaos? Could the entire solar system be fundamentally unstable despite appearing perfectly regular on human timescales? Sleep became elusive as I lay awake contemplating the implications. If three-body motion resisted analysis, what about systems with 4 bodies, or 10, or hundreds? What about the countless particles that composed ordinary matter? The dream of a completely predictable universe was giving way to a nightmare of infinite complexity lurking beneath the surface of apparent natural order. Yet slowly, through months of struggle, a different kind of understanding began to emerge. The three-body problem was teaching me that some of nature's most profound truths might be revealed through our limitations rather than our successes. Perfect predictability might actually represent a kind of poverty, a universe so simple that it held no genuine surprises. Unpredictability might be a feature rather than a flaw, a sign that creation was rich enough to exceed any finite mind's ability to comprehend it completely. I began to see beauty in the mathematical complexity that had initially frustrated me. The three-body equations possessed an intricate structure that revealed new patterns at every level of analysis. Even if I couldn't solve them completely, they showed me aspects of natural law that simpler systems had hidden. Unpredictability became not a failure of mathematics, but a window into the inexhaustible creativity embedded in natural processes.
The navigation chart spread across the Admiralty Conference table in the spring of 1699
Told a story of mathematical humility translated into practical wisdom. Each chart bore my annotations showing regions where lunar position predictions carried larger uncertainties, areas where navigators should exercise additional caution, and recommended procedures for working with approximate knowledge rather than mathematical certainty. Lord Admiral Russell received my report with the weary patience of a man accustomed to disappointment. Sir Isaac, he said, studying the charts with practiced eyes, are you telling me that after 4 years of work the longitude problem remains unsolvable? I chose my words carefully. My lord, I am telling you that the longitude problem cannot be solved with the mathematical certainty we initially sought, but it can be solved well enough to save lives and preserve ships, if we adjust our expectations and methods accordingly. This distinction between perfect solutions and practical solutions had become the central lesson of my struggle with the three-body problem. The moon's motion could not be predicted with absolute precision, but it could be predicted well enough for navigation. Approximate knowledge properly applied was vastly superior to no knowledge at all. The lunar tables I delivered to the Admiralty in 1699 represented a fundamentally different approach to mathematical natural philosophy. Instead of claiming perfect accuracy, they include explicit error estimates for different types of calculations. Instead of providing single predicted positions, they gave ranges of probable positions with associated confidence levels. Instead of promising certainty, they offered the best approximations that careful analysis could provide. Training navigators to use these new methods required overturning centuries of navigational tradition. Sailors had always sought definitive answers to questions of position and course. The idea of working with probability ranges and uncertainty estimates seemed to violate the basic promise of mathematical navigation. If the calculations couldn't provide exact answers, why trust them at all? Captain James Montgomery, one of the Navy's most experienced navigators, voiced the common concern during our training sessions at Portsmouth. Sir Isaac, if you cannot tell me exactly where the moon will be tomorrow night, how can I trust your calculations to guide my ship safely home? I had learned to answer such questions with analogies drawn from daily life. Captain, when you plan to meet a friend in London, do you demand that he specify his arrival time to the exact minute, or do you arrange to meet within a reasonable window, accounting for the uncertainties of travel? I allow for delays and uncertainties naturally. Navigation with approximate lunar tables follows the same principle.
We cannot predict the moon's position to the exact minute,
but we can predict it accurately enough to determine your longitude within a few miles. For a ship approaching the English coast after weeks at sea, knowing your position within 5 miles is enormously better than not knowing your position at all. The practical implementation of approximate methods revealed unexpected advantages over the perfect solutions I had originally sought. Navigators using lunar tables with explicit uncertainty estimates made more conservative decisions about dangerous coastlines. They maintained greater awareness of cumulative errors over long voyages. They developed backup methods for situations where lunar observations were unreliable or impossible. Most importantly, they learned to work with nature's complexity rather than fighting against it. The moon's motion showed irregular variations that reflected the intricate gravitational dance of Earth, Moon, and Sun. Rather than treating these variations as errors to be eliminated, skilled navigators learned to recognize and account for them as natural features of celestial mechanics. The success rate of English naval voyages improved dramatically once these methods became standard practice. Ships still occasionally ran aground or missed their destinations, but at rates far lower than before lunar navigation became available. The approximate solution to the three-body problem was saving hundreds of lives annually and preserving vessels worth thousands of pounds. Letters from sea captains using the new lunar tables provided practical feedback that no theoretical analysis could have anticipated. Captain William Dampier wrote from the Caribbean in 1701, "The lunar method gives me confidence I never had before in deep ocean navigation. Not because it promises perfect accuracy, which would be impossible to verify anyway, But because it provides reasonable estimates with honest acknowledgement of their limitations, I can plan my approach to dangerous waters accordingly. This feedback taught me that practical utility often matters more than theoretical perfection. A method that worked tolerably well in all conditions was more valuable than a method that worked perfectly only under ideal circumstances. Approximate solutions that acknowledged their limitations inspired more confidence than exact solutions that made unrealistic claims about their precision. The longitude problem had forced me to develop what I began calling mathematics of the possible rather than mathematics of the certain. Instead of seeking analytical solutions that provided exact answers, I learned to construct numerical methods that provided good approximations with known error bounds. Instead of demanding mathematical elegance, I accepted computational approaches that yielded useful results through systematic approximation. These new methods found applications far beyond navigation. Cartographers used similar approaches to map coastlines with appropriate uncertainty estimates. Surveyors applied them to land measurement problems where perfect precision was impossible, but good approximation was sufficient. Military engineers adopted them for calculating artillery trajectories where wind resistance and other complications made exact solutions impractical. The deeper lesson was that most real-world problems resembled the three-body problem more than they resembled the idealized two-body problems that had first attracted me to mathematical natural philosophy. Systems with multiple interacting components, whether mechanical, astronomical, or social, typically exhibited complexity that resisted exact analysis while remaining amenable to useful approximation. I began teaching these principles to my students at Cambridge, emphasizing that practical mathematics required learning to work comfortably with uncertainty. The most valuable mathematical skill was not the ability to find perfect solutions to idealized problems, but the ability to find good approximations to realistic problems. Young mathematicians initially resisted this message. They had come to Cambridge expecting to learn methods that would provide certain knowledge about natural phenomena. The idea that uncertainty was a permanent feature of mathematical analysis rather than a temporary limitation to be overcome seemed to diminish the power and beauty of mathematical reasoning. But those who mastered the new approaches discovered that working with uncertainty opened more problems to mathematical analysis than it closed. Systems that were too complex for exact treatment often yielded readily to approximation methods. Problems that had seemed hopelessly intractable became manageable once perfect solutions were no longer required. The transformation was perhaps most visible in my approach to teaching celestial mechanics. Previously, I had focused on two-body problems that could be solved exactly, presenting them as representative of all gravitational phenomena. Students learned to calculate planetary orbits with perfect precision and left my courses believing that all astronomical problems were equally tractable. Now I began with three-body problems, showing students immediately that most natural systems were too complex for exact analysis. They learned approximation methods as fundamental tools rather than unfortunate compromises. They developed intuition about when approximate solutions were adequate and when additional precision was necessary. The results were paradoxical but consistent. Students who learned to work with uncertainty from the beginning became more confident in applying mathematics to practical problems than students who had learned to expect certainty. Acknowledging the limitations of mathematical methods seemed to expand rather than contract their practical utility. By 1703, when I delivered my final report to the Admiralty on the longitude problem, I could claim success of a kind I had never originally envisioned. The three-body problem remained unsolved in the sense that no exact analytical solution existed, but it had been solved in the sense that practical methods for working with three-body systems were now available and proving their value in daily use. Lord Admiral Russell, reviewing 4 years of successful navigation using lunar tables, offered an assessment that captured the essential transformation. In my thinking, Sir Isaac, you promised us mathematical certainty and delivered something more valuable, mathematical wisdom. Our navigators sail with greater confidence now than when they believed their methods were perfect because they understand both the power and the limits of their calculations. The weather prediction experiments I began in 1704 filled my study with barometric instruments, wind vanes, and temperature gauges, arranged in what my housekeeper called the madman's collection. Each morning I recorded atmospheric conditions with the same precision I had once applied to planetary observations, hoping to discover mathematical patterns that would allow prediction of rain, snow, and storm systems days or weeks in advance. The project was born from the same optimistic confidence that had originally attracted me to the three-body problem. If I could understand the forces governing atmospheric motion, surely I could predict weather patterns using the same analytical methods that had worked so well for celestial mechanics. The atmosphere, after all, was simply a fluid system governed by well understood physical principles, temperature differences driving air movement, pressure gradients creating winds, moisture evaporation and condensation producing clouds and precipitation. My initial approach followed the mathematical strategy that had succeeded with two-body problems. I attempted to identify the dominant forces shaping weather patterns and treat all other influences as small perturbations. The sun's heating seemed to drive the primary circulation patterns, with Earth's rotation and seasonal changes providing secondary modifications. Local geographical features and random temperature fluctuations could be handled as minor corrections to the basic mathematical framework. The failure was even more complete than with the three-body problem. Atmospheric motion proved to be a system of staggering complexity, with millions of interacting components operating across scales from individual air molecules to continent-spanning pressure systems. Every cubic foot of air contained countless particles whose individual motions contributed to the collective behavior I was trying to predict. Temperature differences measured in fractions of degrees could amplify over days into massive storm systems or unexpected calms. Within weeks of beginning systematic observations, I discovered that tiny variations in initial conditions produced dramatically different weather outcomes. A morning with easterly winds at 3 miles per hour might be followed by afternoon thunderstorms, while a morning with easterly winds at 4 miles per hour might remain clear and calm. The sensitivity to initial conditions that had frustrated me in the three-body problem appeared magnified thousandfold in atmospheric systems. My correspondence with natural philosophers across Europe revealed that others were encountering similar difficulties with complex systems. Daniel Bernoulli in Basel was struggling to apply mathematical analysis to fluid flow problems. Euler in St. Petersburg was finding that mechanical systems with many moving parts resisted the analytical methods that worked beautifully for simple machines. D'Alembert in Paris was discovering that vibrating strings and membranes produce mathematical equations that seemed to have no closed-form solutions. A pattern was emerging that challenged the fundamental assumptions of mathematical natural philosophy. Simple systems with few interacting components could often be analyzed exactly using the mathematical tools available to us. But systems with many interacting components, even when governed by perfectly understood physical laws, seemed to generate complexity that exceeded any computational approach we could devise. The Weather Prediction Project taught me to recognize this complexity as a fundamental feature of nature rather than a temporary obstacle to be overcome through better mathematics. Atmospheric systems were not poorly understood planetary motions. They were qualitatively different phenomena that exhibited what I began calling essential unpredictability. Essential unpredictability differed from mere ignorance or computational limitations. It arose from the intrinsic structure of systems where small causes could produce large effects through cascading interactions among many components. Even perfect knowledge of the governing physical laws and arbitrarily precise measurements of initial conditions could not guarantee accurate long-term predictions for such systems. This realization forced me to reconsider the entire project of mathematical natural philosophy. Was the goal to find exact solutions to idealized problems, or to develop useful approximation methods for realistic problems? Should we seek mathematical certainty about simple systems or practical understanding of complex systems? Did the power of mathematical analysis lie in its ability to predict, or in its ability to reveal patterns and relationships that might otherwise remain hidden? My weather observations began revealing patterns that were invisible to exact mathematical analysis but visible to statistical approaches. While I could not predict when it would rain next week, I could identify seasonal trends in precipitation. While I could not calculate the exact path of individual storms, I could recognize recurring circulation patterns that shape regional climate. While I could not solve the equations governing atmospheric motion, I could discover empirical relationships between different meteorological variables. These statistical patterns suggested a different way of understanding complex systems. Instead of seeking to predict their exact future states, I could characterize their typical behavior, their range of possible outcomes, and their response to different kinds of external influences. This approach sacrificed the precision of exact prediction in exchange for the robustness of statistical understanding. The method proved applicable far beyond meteorology. Population changes in London parishes followed statistical patterns even though individual births and deaths were unpredictable. Market prices for grain and wool exhibited recurring cycles even though specific price movements could not be calculated in advance. Disease outbreaks spread according to mathematical relationships even though the timing and location of individual infections remained mysterious. I began to see that much of nature operated according to what I termed statistical laws rather than dynamical laws. Dynamical laws, like those governing planetary motion, allowed exact prediction of future states from present conditions. Statistical laws characterize the probable behavior of systems without specifying their exact future evolution. Both types of laws reflected genuine patterns in natural phenomena, but they provided different kinds of understanding and enabled different kinds of practical application. Dynamical laws supported precise prediction for simple systems. Statistical laws supported reliable planning for complex systems. The intellectual adjustment required to embrace statistical thinking proved enormous. My entire education in natural philosophy had emphasized the search for exact solutions and precise predictions. The idea that useful knowledge could emerge from explicitly acknowledging ignorance seemed contradictory to the foundations of rational inquiry. But the alternative was to limit mathematical analysis to artificially simple problems that bore little resemblance to the complex systems that actually shaped human experience. Weather, population dynamics, economic fluctuations, disease transmission, and countless other phenomena of practical importance involved too many interacting components to yield to exact mathematical treatment. If mathematics was to remain relevant to natural philosophy, it had to develop methods for working productively with complexity and uncertainty. My teaching at Cambridge began reflecting this broader vision of mathematical natural philosophy. Students learned exact methods for simple systems alongside approximation methods for complex systems. They practiced statistical analysis alongside dynamical analysis. They developed comfort with probabilistic reasoning alongside deterministic reasoning. The response from younger scholars was encouraging. Students who learned both approaches seemed better equipped to tackle real-world problems than those who had mastered only exact methods. They showed more creativity in applying mathematical reasoning to novel situations. Most importantly, they demonstrated wisdom in recognizing which types of problems were amenable to which types of analysis. By 1706, I had accumulated enough experience with complex systems to begin articulating general principles about the relationship between mathematical analysis and natural phenomena.
Some systems were simple enough to permit exact analysis and precise prediction. Others were complex enough to require statistical analysis and probabilistic prediction.
Still, others exhibited intermediate behavior that called for hybrid approaches combining elements of both methodologies. The art of mathematical natural philosophy lay in recognizing which approach was most appropriate for each particular problem. This required developing intuition about the structure of natural systems that went beyond familiarity with mathematical techniques. It demanded what I began calling mathematical wisdom to complement mathematical skill.
The teaching notes I prepared for my Cambridge lectures in 1708 reveal the struggle of a man trying to convey revolutionary ideas to minds trained in certainty. Each page bears evidence of multiple revisions as I searched for ways to explain why acknowledging mathematical limitations could be more powerful than claiming mathematical omnipotence. My students, brilliant young men who had come to Cambridge expecting to master the secrets of natural philosophy, resisted the notion that some secrets might be permanently beyond human reach. But Sir Isaac, young William Whiston challenged during one particularly difficult lecture. If we cannot predict the precise motion of three bodies under gravitational attraction, how can we claim to understand gravitation at all? Surely understanding means the ability to calculate all consequences of our principles. Whiston would later succeed me in the Lucasian chair, and his question captured the generational divide I was trying to bridge. Students trained in the tradition I had helped establish equated understanding with predictive power. They expected mathematical natural philosophy to provide certain knowledge about all natural phenomena. The idea that genuine understanding could coexist with fundamental unpredictability seemed to them like a contradiction in terms. I had learned to address such concerns through carefully chosen analogies that connected mathematical concepts to familiar human experience. Mr. Whiston, do you understand the nature of human friendship? I believe I do, Sir Isaac. Can you predict with mathematical precision how your friends will behave in any particular situation? Of course not. Human behavior is far too complex and variable. Yet your inability to predict your friend's actions does not prevent you from understanding friendship, does it? You recognize the patterns, the underlying motivations, the general principles that govern social relationships. Understanding and prediction are related but distinct forms of knowledge. The parallel between social relationships and physical systems became central to my pedagogical approach. Students could readily accept that human behavior was too complex for exact prediction while remaining perfectly comprehensible in general terms. The challenge was helping them see that natural systems could exhibit the same combination of intelligibility and unpredictability. Some students embraced this perspective more readily than others.
Those with practical experience in navigation, surveying, or mechanical arts seemed comfortable with approximate methods and uncertain outcomes. They had learned through direct experience that useful knowledge rarely came with perfect precision. Mathematical techniques that provided good approximations struck them as valuable tools rather than disappointing compromises. But students with purely academic backgrounds often struggled to abandon their expectation of mathematical certainty. They had been attracted to natural philosophy precisely because it promised exact knowledge, in contrast to the ambiguities and uncertainties of other fields of learning. The idea that mathematics itself contained irreducible uncertainties challenged their fundamental assumptions about the nature of rational inquiry. Edmund Stone, one of my most gifted students, voiced this concern with characteristic directness. Sir Isaac, if mathematical natural philosophy cannot provide certain knowledge, what distinguishes it from mere speculation or opinion? Why should we trust mathematical reasoning more than common sense or traditional authority? The question forced me to articulate more clearly what made mathematical approaches valuable even when they could not guarantee perfect accuracy. Mathematical reasoning, I explained, provided systematic methods for improving our approximations, quantifying our uncertainties, and testing the consistency of our explanations. Even when mathematical analysis could not produce exact answers, it could distinguish between better and worse approximations, more and less reliable predictions, stronger and weaker explanations. Consider, I suggested to Stone, the difference between a navigator using lunar tables with known error bounds and a navigator relying solely on intuition and experience. Both face uncertainty about their exact position, but one has systematic methods for reducing that uncertainty and realistic estimates of its magnitude. Mathematical reasoning does not eliminate uncertainty, but it helps us work more effectively with the uncertainty that exists in all human knowledge. This distinction between eliminating uncertainty and managing uncertainty became fundamental to my revised approach to teaching natural philosophy. Students learned to calculate error bounds alongside primary results. They practiced estimating the reliability of different types of approximations. They developed skills in recognizing when additional precision was necessary and when existing approximations were adequate for practical purposes. The pedagogical transformation required rethinking not just what students learned, but how they learned it. Traditional mathematical education emphasized finding exact solutions to well-posed problems. Students worked through increasingly difficult exercises that always had definite answers that could be verified through established procedures. Success meant arriving at the correct solution through proper application of mathematical techniques. But education for working with complex systems required different skills and habits of mind. Students needed to learn comfort with ambiguous problems that might have multiple reasonable approaches. They had to develop judgment about when to invest effort in improving precision and when to accept existing approximations. Most importantly, they needed to cultivate intellectual humility about the limits of mathematical reasoning while maintaining confidence in its power within those limits. The results of this educational experiment were remarkable but not uniform. Students who successfully adapted to the new approach showed greater creativity in tackling novel problems. They demonstrated better judgment in applying mathematical techniques to practical situations. They exhibited more realistic expectations about what mathematical analysis could and could not accomplish, but they also showed more caution about making strong claims and more awareness of the assumptions underlying their reasoning. A smaller group of students never adjusted to working with uncertainty and approximate methods. They continued to seek problems that admitted exact solutions and grew frustrated when confronted with the inherent complexity of realistic systems. Some transferred to other fields where traditional certainties seemed more secure. Others completed their studies but applied their mathematical training only to highly idealized problems that bore little resemblance to actual natural phenomena. The difference between these two groups seemed to reflect deeper temperamental differences rather than mere differences in mathematical ability. Students who thrived with uncertainty appeared more comfortable with ambiguity in general. They showed greater tolerance for provisional conclusions, more flexibility in revising their beliefs when confronted with new evidence, and more willingness to acknowledge the limits of their knowledge. By contrast, students who struggled with uncertainty often exhibited what I began recognizing as a kind of intellectual rigidity. They preferred definite answers, even when those answers were based on unrealistic simplifications. They showed reluctance to revise established methods, even when those methods proved inadequate for new types of problems. Most troubling, they sometimes claimed more precision than their methods could actually provide, preferring false confidence to honest acknowledgement of limitations. The broader implications for the future of natural philosophy became clear through observing these generational differences. The students who learned to work comfortably with uncertainty would be better equipped to tackle the complex systems that increasingly demanded scientific attention. Weather prediction, population dynamics, mechanical systems with many interacting parts, and countless other phenomena would require mathematical approaches that could handle complexity without demanding certainty. But the transition would not be automatic or universal. Each generation of scholars would face the choice between seeking artificial certainty about simple systems or developing practical wisdom about complex systems. The future of mathematical natural philosophy would depend on cultivating intellectual virtues that complemented mathematical skills, humility about the limits of human knowledge, wisdom in choosing appropriate methods for different types of problems, and courage to acknowledge uncertainty without abandoning the quest for understanding. My teaching notes from this period reveal growing optimism that these intellectual virtues could be cultivated through proper education. Students were not born with fixed attitudes toward uncertainty and complexity. With appropriate guidance and encouragement, they could learn to see mathematical limitations as opportunities for deeper understanding rather than failures of rational inquiry.
The final entry in my observatory logbook dated March 15, 1725 consists of only a few lines written in the shaky hand of an aging man who had spent more than 60 years wrestling with the mysteries of natural philosophy.
Today marks 30 years since I first encountered the three-body problem, I wrote. What began as a mathematical challenge became a transformation of understanding that continues to shape every aspect of my thinking about natural law, human knowledge, and the relationship between simplicity and complexity in God's creation. Rereading those words now, I am struck by how completely the three-body problem changed not just my mathematics, but my entire relationship with knowledge itself. The young man who had confidently promised the Admiralty a complete solution to lunar motion seems like a different person, someone whose certainties I can barely remember sharing. The transformation began with mathematical failure, but grew into something much more profound. Learning to work productively with uncertainty taught me that some of nature's most important truths emerge not from our ability to control and predict, but from our willingness to engage respectfully with complexity that exceeds our analytical capabilities. The three-body problem became a teacher whose lessons extended far beyond celestial mechanics. In the decades since that initial struggle, I have watched other natural philosophers build upon the insights that emerged from acknowledging mathematical limitations. Euler's work on fluid dynamics embraced approximate methods as fundamental tools rather than regrettable compromises. Daniel Bernoulli's analysis of probability showed how statistical reasoning could provide genuine understanding of uncertain events. D'Alembert's investigations of vibrating systems revealed mathematical beauty in problems that admitted no exact solutions. Each of these developments validated the central lesson of the three-body problem, that mathematical natural philosophy gained power by accepting rather than denying the complexity inherent in most natural systems. The field matured by learning to distinguish between problems where exact solutions were possible and problems where approximate methods were not just adequate but more appropriate to the underlying phenomena. The practical consequences have been enormous. Navigation using lunar tables based on approximate solutions to the three-body problem has saved countless lives and preserved thousands of ships. Weather prediction using statistical methods has helped farmers plan more effectively and warned coastal communities of approaching storms. Engineering projects employing approximate analysis of complex mechanical systems have built bridges, mills, and machines that serve human needs reliably despite being designed without perfect mathematical certainty. Perhaps most importantly, acknowledging the limits of mathematical prediction has opened space for approaches to natural philosophy that complement rather than compete with exact analysis. Careful observation of phenomena too complex for theoretical treatment has revealed patterns in relationships that pure mathematics might never have discovered. Experimental investigation of systems beyond analytical reach has uncovered principles that inform both theoretical understanding and practical application. The philosophical implications continue to evolve in ways I could never have anticipated. The recognition that deterministic systems can exhibit practically unpredictable behavior has begun influencing how natural philosophers think about causation, explanation, and the relationship between scientific knowledge and divine providence. Some see unpredictability as evidence for continued divine involvement in natural processes. Others view it as a natural consequence of the complexity that emerges when simple laws govern systems with many interacting components. I find myself drawn toward a middle position that sees both perspectives as partially correct. The three-body problem taught me that nature operates according to discoverable laws while remaining full of genuine surprises. This combination seems worthy of a creator who values both order and novelty, predictability and freedom, rational structure and creative possibility. My students from the early years of this century now hold chairs at universities across Europe. Their letters describe research programs that would have been impossible without the intellectual framework that emerged from wrestling with mathematical uncertainty. They investigate atmospheric circulation patterns, analyze population dynamics, study the behavior of complex mechanical systems, and tackle dozens of other problems that require comfort with approximate methods and statistical reasoning. More encouraging still, they report that their own students seem to adapt even more readily to working with uncertainty and complexity. Each generation appears more comfortable with the idea that useful knowledge can emerge from acknowledging rather than denying the limits of human understanding. The intellectual virtues necessary for productive engagement with complex systems, humility about knowledge claims, wisdom in choosing appropriate methods, courage to work with uncertainty seem to be spreading through the community of natural philosophers. Yet challenges remain. The human desire for certainty runs deep, and each new generation includes scholars who prefer the false security of oversimplified problems to the honest complexity of realistic systems. The tension between seeking exact solutions to artificial problems and developing approximate methods for real problems continues to shape debates about the proper methods and goals of natural philosophy. I have come to see this tension as productive rather than problematic. Natural philosophy benefits from including both approaches. Exact analysis of simple systems reveals fundamental principles and provides baselines for judging the accuracy of approximate methods. Approximate analysis of complex systems develops tools for engaging with phenomena of practical importance and tests the limits of theoretical understanding. The three-body problem taught me that the goal should not be to eliminate this tension, but to manage it creatively. The most powerful mathematical natural philosophy emerges from the productive interaction between exact methods and approximate methods, simple systems and complex systems, theoretical understanding and practical application. As I approach the end of my active research career, I find unexpected peace in the limitations that once frustrated me so deeply. The three-body problem can never be solved exactly, but this limitation has opened pathways to understanding that perfect solutions might have closed. Weather can never be predicted with complete accuracy, but statistical approaches to atmospheric behavior have practical value that exceeds perfect prediction of idealized systems. Most profoundly, learning to work with uncertainty has taught me that some of the universe's greatest beauties emerge from phenomena that resist complete human comprehension. The intricate dance of three gravitating bodies exhibits mathematical structures of stunning complexity that no analytical solution could fully capture. Weather systems display patterns of organization across multiple scales that statistical methods can characterize but never perfectly predict. These phenomena invite a kind of understanding that combines intellectual analysis with aesthetic appreciation, mathematical rigor with humble recognition of natural mystery. They teach us that the universe is simultaneously comprehensible and inexhaustible, governed by discoverable laws yet full of genuine surprises. The moment I tried to predict where three things would be tomorrow, I discovered truths about the nature of knowledge itself that no amount of successful prediction could have revealed. The universe keeps secrets not because it is fundamentally unknowable, but because it is richer than any finite understanding can encompass. That richness, I have learned, is not an obstacle to knowledge, but an invitation to wonder.